Assalamualaikum and a very good day to everyone. So today we will continue our last diode application, which is regarding on the Zener as a regulator, right? So here is the learning outcome. You should know how the operation of Zener diode, okay, as a voltage regulator, and also you should know how to analyze Zener regulator circuit, okay. So this is very important, and what are the right procedure and the right techniques in order to solve the functional blocks in power supply. All right. Now let's look what is the voltage regulator. So as I explained previously, all right, a voltage regulator is the function where for us to achieve our objective, which is to have a maintain DC output voltage based on the Zener diode voltage. Okay, so the function is to maintain a DC output despite changes in input voltage or load. All right. Okay, so now let's look what is the basic power supply. All right, so for a basic function of DC power supply is to convert an AC voltage to a smooth DC voltage, and we have discussed this in our previous class. We have looked the function of the rectifier, okay, where it will change the pulsating, all right, from the AC waveform into a pulsating DC waveform. And then we have a filter, right? So this is a filter, where a filter will then eliminate the fluctuations of the waveform, right? And at last, in order for us to have a smooth DC voltage, we need to apply a regulator. All right, so this is a complete blocks of a DC power supply. Okay, all right, so what is a voltage regulator? It consists of a component of a Zener diode. Okay, you should know this. It consists of a component of Zener diode. So this is the Zener diode. Okay, right, it's very easy to know it is a Zener diode because you can see there is a Z shape of the diode. All right, and then we have an RS resistance. Okay, so this RS is to limit the value of current flowing inside this Zener diode. Okay, so this is the function of the RS resistance. All right, so these are the components needed, okay, for a regulator. All right, so the main component, of course, a Zener diode, but we also have another component which is called as a resistance, okay, which is a limits resistance, usually denotes as RS. All right, and then we have the output, which is connected to a load resistance lah. All right, so these are the types of the regulator voltage. Okay, if you can look here, so these are the types of regulator voltage regulators, right? And this is the specs based on the type of voltage regulator. All right, so these are the basic function of a Zener diode, where to maintain a specific voltage across its terminals. Okay, so across these terminals, you're gonna have a specific voltage within given limits or line or load change. All right, so it used to provide a stable reference voltage, meaning that you're gonna have a stable voltage, okay, for use in power supplies and other equipment. And the Zener diode will adjust its impedance, okay, the impedance of the Zener diode based on the varying input voltage, okay, varying input voltage. All right, so this input voltage, and also based on the RL resistance loads here. Okay, so based on these two, info, which is the input voltage and the load resistance value, right, Zener diode will adjust its impedance. All right, so Zener has a finite range of operation. Usually we call it as a Zener current, right, where it will increase or decrease directly based on the voltage input. And okay, meaning that if your voltage input is increasing, your Zener current also will increasing. Okay, however, will increasing. Okay, my pen is not working right here. Okay, however, it will work inversely with the varying loads, meaning that if the loads, okay, load resistor here is high, okay, then your Zener current will gonna be low at this part. All right, okay, it works inversely. All right, so it works it will increase or decrease directly, meaning that it works proportionate to the voltage input changes. However, it will work inversely with the varying loads. All right, and I believe you have familiar with this as well. I have shown to you earlier. Okay, so these are the characteristics of the Zener diode voltage regulator, where IZK is the Zener knee current, IZT is the Zener test current, alright, and IZM is the Zener maximum current. So if it works more than this current, okay, if it works more than this value of a Zener maximum current, your Zener will gonna be breakdown. All right, so in the components of a circuit, so this is where your circuits will gonna look like. Okay, where you're gonna have a transformer. Okay, basically you're gonna have a transformer here. Okay, you're gonna have a transformer here. All right, and this transformer based on what kind of ratio. All right, okay, and then the value of the secondary of the transformer will gonna be the input voltage to your rectifier. Okay, so in this case you can see 4 rectifier here, okay, 4 diodes here, so meaning that you're gonna have full wave rectifier. Okay, all right, full wave rectifier. And we also have a filter. You can see a capacitor here. So in this case here is the where your voltage will gonna be filter. Okay, meaning that the fluctuation will gonna be eliminates. Right, and then we're gonna have this R and this VZ. Okay, the R here, okay, the R here and the VZ here, both of this is known as a Zener, okay, regulator. All right, and then at the end, okay, you're gonna have a load at your output, load resistor. Okay, so Zener diode as a voltage regulator. So now let's look how it works as a voltage regulator. So it will works as voltage regulator only when it is on stage. All right, when it is on state. All right, so how to determine either the Zener is on or the Zener is on or off? So it depends how much the value of the currents flow through this Zener. Okay, it depends on how much value of currents flow inside this Zener. So if the Zener flow, the value of currents is within the operating voltage of the Zener, then the Zener will gonna be turning on. Okay, if not, the Zener will gonna be turning off. All right, so Ri, so now let's look at the function of each components here. So Ri, okay, the Ri, which is this resistance, the function of this resistance is to limit the Zener current, okay, to ensure the currents that flow in the Zener will be limited. All right, so Ri is the limit, is to limit the Zener current Iz so that it is less than the maximum current. So this is to avoid the Zener becomes breakdown, okay, or will be in a breakdown region. Right, so it makes sure that the value of Iz will not go to the value of IZM. All right, ZM. And to avoid the Zener diode from getting damaged. So the characteristics of the Zener diode determines the value of the VL. So if the Zener is turning on, so the VL value, okay, your output voltage value at the load resistance will gonna be same as the Zener voltage, right? So these are the famous formula that you need to remember, okay, which is the value across okay, value across load resistor current, okay, value of current across load resistor, which is IL, we're gonna be, okay, IL here, we're gonna be VZ, all right, which is the value of the Zener if the Zener is turning on, yeah, value of a Zener voltage divided with the value of load resistor. Okay, this is only true if the Zener diode is turning on, right? So if the turning on, we know the voltage across the load resistor is the same as the voltage of Zener, right? And in that case, we can measure the value of I1, alright? So the value of I1 will gonna be the value of input voltage VPS minus with the VZ, because we have a voltage difference there, okay, VPS minus with the VZ over RI, so we can know what is the value of currents flow in the resistor RI, okay. And in that case, we also know about the Kirchhoff current law, okay, Kirchhoff current law, which is KCL, okay, Kirchhoff, oh my god, KC, oh my god, sorry with the handwriting, I'm not sure what's wrong with my pen, K, C, okay, L, alright, okay, I hope you can read, yeah, this is L, Kirchhoff current law. So Kirchhoff current law said that in this case, yeah, I1 equals to IZ, okay, IZ plus with IL, okay, right? So in this case, this formula is by applying the Kirchhoff current law lah. Alright, so now let's look at the voltage regulation. So how well the regulation is performed by a regulator is measured by its regulation percentage. Alright, so for these slides, you need to know only by the theoretical, okay? So we have two types of regulation. One, it is known as line regulation, and another one is known as load regulation. Okay, what it means by line regulation and what it means by load regulation. Okay, to know this, first of all, we need to analyze either the Zener is turning on or turning off. Okay, now let's look at this case. So in this case, the question asks about the Zener diode voltage regulator. Okay, how to determine whether the Zener act as a regulator? Okay, if it is act as a regulator, meaning that the Zener is turning on. But if it is not act as a regulator, it means that the Zener is turning off, right? So how to determine that? Okay, first of all, so this is your input voltage. Okay, you are given an input voltage here, all right, and this is your Zener. Okay, this is your Zener diode, okay, and this is your load resistor. Okay, so normally your load resistor is looked as at this part, right? Right? Alright, but in this case, we are bringing the load resistor to this side. Okay, to this side, right? So that you can see much easier. Okay, so to know this, we need to know what is the voltage across this load resistor. Okay, so to know the voltage across this load resistor, we can use the Thevenin theorem, which I have introduced to you earlier. Okay, in our classes, I have introduced to you when we want to solve the diode circuit analysis, right? So the Thevenin theorem, okay, we can find the value of new voltage, which is known as V Thevenin. So where is this V Thevenin we're gonna be at? So it will gonna be our new source voltage, right? Which is, this is the voltage across the RL resistance, alright? So how to find that? So to know what is the voltage across this RL resistance, okay, we're going to use the voltage divider rule, which is Vs, alright, is equals to RL, okay, over, which is, this is RL, the one that we're gonna that we want to determine, right? RL over the value of resistor, RL plus RS. So in this case, we're gonna have new value of voltage, alright, which gonna be called as V Thevenin, and the new voltage, a new resistance value. So RS and RL here we're gonna be in a parallel, alright. So we can calculate the value of the parallel of RS and RL. So it's gonna be as R Thevenin, okay, Thevenin resistance value, alright. And in that case, we can make or simplify our circuit to be, alright, we can simplify our circuit to look as such. So this is the simplified version of the circuit, and we still gonna have our VZ, because our VZ is not included inside of our calculation here. In this calculation here, VZ is not considered at all. So at your simplified circuit, you need to add your VZ. Alright, so now how we want to determine the Zener is on or off. So if the value of V Thevenin, the one that we have calculated earlier here, is lesser than the operational voltage of the VZ, okay, you don't have to worry, because usually the VZ will be provided to you. Okay, VZ will gonna be provided to you, and they ask you either the VZ is on or off, alright. So if the V Thevenin is lesser than VZ, so the regulation will not happen, and in this case we said that the Zener is actually turning off. Okay, we said that actually the Zener is turning off, yeah. Alright, so however, if the V Thevenin that you have calculated earlier is larger than VZ, larger or same value, it must be slightly larger, okay, larger than the value of V Thevenin, alright. So larger than the value of VZ. So we said in this case our Zener diode function as a voltage regulator, or on the other word, it is in a on state, alright. So if the voltage across Zener diode is between 0 and VZ, the Zener diode is operating in the reverse bias, okay, thus it does not function as regulator, alright. But the VTH, V Thevenin, must at least reach the same value as VZ, which is V Thevenin must be larger than VZ, so that the diode can function as a voltage regulator, okay, as it now operating in the reverse breakdown. Okay, so if the value of VTH is larger compared than VZ, so now in that case you gonna be, the diode will gonna be in a reverse bias condition. So if it is a reverse bias condition, we know it is actually a on lah, the diode, Zener diode is on here. Okay, so I hope I make it clear that if the VTH is larger than VZ, So we know in that case your Zener will gonna be work or function as an voltage regulator. Okay, so that is how we want to determine either the Zener is on or the Zener is off. Okay, now let's look at the example number 1. So example number 1, determine whether the Zener diode is function as a regulator or not, or in other words, it is in a on state, okay, on state, or in off state. Okay, alright, so there are two methods, which is basically both of this method is the same actually. Okay, first method we can use the Thevenin method. Alright, so the Thevenin methods here, we have our input voltage is 15. Okay, input voltage is 15, and we have our load resistor here is 150. So we want to find the value of V across the load resistor, so we can apply the V Thevenin. Okay, alright, I'm writing it here. Yeah, I'm not sure why the pen is somehow, it's very hard to write. So V Thevenin, so V Thevenin will be equals to, alright, our input voltage, which is 15, okay, 15, it's going, okay, okay, 15 over the load resistance value, which is 150. It's very difficult to write number 5. 150, okay, 150 over 150 plus, okay, plus bit 100. Okay, so you can use your calculator. What is the value of the V Thevenin that you got? Okay, so gonna be 15 over multiply with 150 divided with 250. So you will get the value of your V Thevenin is 9 volts. Right, 9 volts. Oh my god. Okay, so you get your V Thevenin is 9 volts. Okay, it's very difficult to write, I'm not sure why. Okay, 9 volts. Okay, don't forget to write volts here. Okay, right, 9 volts. So in this case, we can compare this value 9 volts and this 10 volts value. So our V Thevenin is lesser compared to, okay, it is lesser. Okay, it's very difficult, lesser. Okay, lesser than 10 volts. Okay, okay, 10 volts. So it is our Zener. You can see the answer here. The Zener is off. Okay, and what is the value of R Thevenin? R Thevenin you can calculate lah, which is RS 100. Okay, 100. Okay, 100 parallel with, okay, I hope you can understand. Yeah, I have a very I have a difficulty with my pen here. Okay, parallel with 150. Okay, 150. Alright, so you should get 160 ohm. All right. Okay, so now you can try the second example here using the Thevenin theorem. You should get the value of V Thevenin is 12 volts, and if we compare this value of 12 volts and the VZ here, your diode should be turning on. Okay, so in this case the value of the the value of the the output, V output here will be according to the value of VZ lah. Alright, and the value of R Thevenin will no changing at all. Alright, and then what else? Okay, so you can see. Alright, now another method. Okay, so another method. So actually for me, this method is look same as the Thevenin theorem. Alright, so method number 2, instead of it names as Thevenin theorem, it is actually using voltage across zener when it is open. So how to use this method is usually we assume that this zener is in an open circuit. Okay, in an open circuit. So if it is an open circuit, your zener will gonna be removed and it will gonna be looked as such. So meaning that your currents will straight away will flow to here across the RL. So we can measure or determine either the zener is turned on or turned off by measuring the voltage across RL. Okay, which is also known as voltage across the zener. Voltage, laser. Okay, voltage. Okay, this is a voltage across the zener when this zener is in open condition. Okay, so determine the state of zener diode by removing it from the circuit and calculate the voltage across that. So voltage across that, we're gonna be, if you look properly, you can see that it is actually the same as the Thevenin theorem. We're gonna be voltage divider as well. We're gonna use the voltage divider rule. We're gonna be VI, okay, the voltage of this source, okay, multiply with the value of RL, which is the load resistor, over the total resistance inside that particular circuit. All right, and yeah, so in this case, if the voltage that you have calculated is larger than the VZ value, so in this case we said that your zener is on condition, and if your V is lesser than the VZ value, then your zener will gonna be in an off condition, which is if it is off condition, it is remain as an open circuit lah. Alright, but if it is an on condition, instead of open circuit, we need to replace it with a voltage. Alright, so now let's look at the types of zener circuit analysis. So there are 3 types, which is, the first one is the most famous one, where the value of voltage source and the load resistance is in a fixed value. Okay, the second value, the second type is when your voltage source Vs is fixed, however the load resistance value is in a variable conditions. Okay, so in this case, it means that your load resistance is not fixed. It has a range of resistance value. Alright, so in this case we said as load regulation, because your load now is changing, so we said as load regulation. The third type is known as line regulation, where in this case your Vs is variable, is changing, and your load resistance is in a fixed condition. Right, so all of these 3 you need to know, because this is a very famous condition of a zener circuit analysis. Alright, so let's look at these slides. Okay, where you're gonna have the fixed Vs and RL. Okay, both of your source and load is in a fixed condition. If both are in a fixed condition, you can choose to apply using the Thevenin theorem or the load resistance, the Thevenin theorem or V across the open zener method to solve the circuit that we have learned just now. Okay, so if your V that you have determined is larger than the value of zener, meaning that your zener is turning on, and if your V that you have determined is lower than the zener voltage, so in that case it means that your zener is turning off. Alright. Okay, so there are two methods that you can use. You can use the Thevenin or the voltage across the open zener. Okay, so now so this is the same. Alright. Okay, for the explanation, if your zener is in on condition, okay, so your zener is regulating, right? So if your zener is in an off state, meaning that your zener is not regulating, and then from here we can calculate the value of current. So the value of current IR, okay, we're going to use the KCL, Kirchhoff current law. It's going to be IR is equals to IZ plus with the IL, right? And if you want to determine the value of IZ, of course it will gonna be IR minus with the value of IL. So since that we know if the zener is turning on, so the voltage across RL, which is the VL voltage, will be according to the zener voltage. So if we know the value of voltage, value of RL is also provided to us, we can find the value of current, load current. Alright, so if we know the value of load current, we can use the KVL, Kirchhoff voltage law, to find the value of VR, right? So VR is equals to IR multiply with R. So alright, if we use the KVL, we can find the value of IS, and then in order to determine IZ, we're gonna be IR, yeah. So in order to determine the IZ, we're gonna be IR minus with the IL. And then once you know how much the current flowing inside the zener, then we can always determine the value of power. Okay, so power, I think you also should know this. Okay, how to calculate power? Power is equals to V, voltage, right? It's very difficult to write like this, yeah. V multiply with I, right? So voltage is based on the voltage of the zener, and then current I will gonna be the value of IZ. Alright, so if your zener is in a off state, okay, if in an off state, of course it's easier. Your IZ here will gonna be 0, your PZ also will gonna be 0 because it is an open circuit. Alright, so if that is okay, if I leave this example for you to solve, alright, because I think this is a very straightforward. Okay, I just show for you to the A1 here. In A, so determine the VL. So for us to determine the VL, right, we want to determine the VL, so of course we can use the voltage divider rule, alright, which is VL, right. It's very difficult because that's why I don't want to write too much. Okay, VL, okay, VL is equals to, alright, is equals to 16, which is your V in, alright, I hope you can see that this is a 16 over, alright, RS, which is over RL 1.2K, 1.2, yeah, 1.2K, okay, over 1K plus 1.2k. Okay, so this is 2, yeah, 2k. Alright, so it's equals to, so you can use your calculator. So it's gonna be 16 multiplied with 1200 divided with 2200, so you will get 8.727. So it's same lah, 8.73. so that is your VL. So to find your VR, we can use the KVL. KVL. Okay, you can use the KVL. So your current will flow inside here. Okay, so from here we can determine lah your zener now is on or off. So your VL is 8.73, your VZ is given as 10 volts. So VL is lower than your VZ, right? So your zener here is turning off. So if it is turning off, so here we're going to be an open circuit. So if here is going to be open circuit, you apply the KVL, your KVL will going to be negative 16, okay, plus with VR plus with VL, right, equals to 0. Alright, so the value of VL is the one that you have determined earlier. The value of VR the one that you can get lah. Alright, so you will get your VR is equals to 7.27. Alright, and since your zener is turning off, so your IZ is equals to 0 and your PZ is equals to 0 as well. Okay, and I leave it to you for you to repeat the value when the load resistance is equals to 3 ohm. Okay, right, so these are the answer that you should get, and I leave it to you guys to calculate by yourself. Yeah. Alright, so now let's look at another condition when your source voltage is in a fixed condition and your load resistance in a variable conditions, meaning that it has a range of value, it is not fixed. Okay, so now let's look at this here. So current across this resistance, the zener resistance here is known as I1. Okay, so here is I1. Current that is across the zener diode is known as IZ, and let's denote as current that is flowing across RL here is known as IL. Okay, it's known as IL. Alright, so okay, if your RL here, okay, if your RL here is larger than the value of RL minimum, okay, then your zener diode is in on condition. Okay, so because of why? Because in that condition your RL here will gonna be too big. Okay, the value of the resistor here is too big. If the value of the resistor here is too big, so what will happen? Okay, what will happen? Current will avoid to across this area, right? Because the resistance is too big. So of course, all the current of I1 will directly flow to IZ instead of IL, because the resistance here is too big. So if your RL is larger than RL meaning that your zener diode will be on, so that the VL voltage across the load resistance will equal to the zener voltage. And in that case, we said that all current will flow throughout this zener diode. Okay, so in that case, we know I Zini, which is the minimum, the knee current of the zener, will gonna be 0 milliampere, right? Because no current will flow inside here, so the minimum current for this zener to turn on is actually 0 milliampere. All right. Okay, so now let's look on the Now let's look on the conditions. Yeah, calculate the IZ using the KCL, Kirchhoff current law. Two conditions. Okay, there are two conditions due to constant I1. Okay, so now let's assume that I1 is constant. Okay, when your I1 is constant, we know KCL said I1 is equals to IZ plus IL, where how to find the I1? I1 is equals to Vs minus Vz if your Vz is turning on. Now is your Vz is turning on. Okay, if your Vz is turning on, I1 can be calculated by Vs, which is the voltage source, minus the voltage zener voltage over the Rs. Then you will get a constant of I1. Your I1 will gonna be always constant. Okay, remember, yeah, when you have a fixed Vs, when your source voltage is fixed, your current I1 also will gonna be constant. The only current that will not be constant is the current of IZ and IL. Current of IZ and IL will be depending on what is the value of the resistor RL. If the value of resistor RL is too high, meaning that more current will flow at IZ, less current will flow at IL. Okay, in some cases IL will gonna be completely zero. Okay, but if the value of RL is minimum, okay, less resistance value, what will happen? I think you can guess already. IZ will become zero, more current will flow through IL. Okay, so these are the condition. Okay, so if RL here, okay, I want to make it an highlighter here. Okay, if RL here is equals to RL minimum, meaning that the value of the resistance is very low here. Okay, the value of resistance is very low. It's gonna be your IL will gonna be IL maximum, because when the resistance here is low, current will flow. Kan? Current will flow when there is value of resistance is low. Okay, so your IL will gonna be IL maximum, and your IZ will gonna be IZ minimum. So less current will flow at the zener. But if your RL is in a maximum value, RL is equals to RL max, the value is larger, then your IL will gonna be IL minimum and your IZ will gonna be IZ maximum. Alright, so these are the cases that you need to remember. Okay, so now let's look at this slide, right? So this is what it means. Okay, your I1 is equals to IZ plus IL, where your Vs is equals to I1 Rs, which is the value of current, multiply the value of resistor, okay, plus with the value of Vz. This is when your zener diode is turned on. Yeah, so you will get the value of I1 in a constant value. Alright, so if your RL in a minimum value, okay, so your RL is minimum. Okay, I mark it. Where is your IL? Yeah, so here is your IL. Okay, so here is your IL, right? So your IL will gonna be in a maximum, and your IZ will gonna be your IZ minimum. So so when your IL is in a maximum, okay, maximum, I put it arrow as max, yeah, maximum. Okay, your IZ will gonna be the value of minimum. Alright, so when your IL is maximum, we know, yeah, V is equals to IR. So this is our Ohm's law. Okay, R. Right, R, ya, this is R. Susahnya nak tulis R. Sekejap. V equals to I. Okay. R. Okay. So when your IL is when your IZ is minimum, okay, when your IZ is minimum, it's gonna be I1. How to calculate your IZ minimum? we're going to be I1 minus IL maximum. So you can see when your RL we're going to be load regulation, which is it has a variable range. It has a minimum and maximum range. Your IZ also we're going to have minimum and maximum range lah, yeah. So for you to calculate your IZ mean, you need to I1, which is the constant value, okay, I1 need to be minus with the IL max, so you will get your IZ mean, okay. And for you to get your IZ max, okay, for you to get your IZ max, it will be I1 minus with the IL mean. And how you want to get your IL mean? IL mean is when your RL in a maximum value, okay, RL in a maximum value, right? So then you will, once you able to determine your IZ max, so of course you can also you will then let your answer have a in a range lah. Your IZ then we're gonna be in a range lah, which is alamak, which is in a range of mean, okay, so this is mean, and it cannot go to the maximum value lah. Okay, so this is max. Okay, so this is max. Okay, so your IZ will gonna be in a range answer. Alright, so now let's look at example number 3. Alright, so example number 3, what is the IL max and IL mean to maintain the regulation? What is the minimum RL? And they ask what is the minimum RL, and given the rated value, so these are the range of the current that should flow inside the diode. The minimum current value is 1 milliampere and the maximum current value is 50 milliampere, and the voltage zener is 12 volts. Alright, so the first solution, okay, when your RL in a RL max, meaning that it is an infinity value, okay, when your RL here is in a maximum, so of course there gonna be no current that is flow in IL, right? So your IL will gonna be, your IL mean will gonna be 0 ampere, and your IZ, okay, since there's no current flow here, of course your IZ will gonna be IZ max, right? Your all the current will gonna be flow into IZ, perhaps most of the current, so your IZ max will equals to IT, right? Sebab tak ada current will gonna flow here, right? When your IZ max is less than 50 milliampere, okay, when your IZ max is less than 50 milliampere, so that RL can be removed without disturbing regulation. Alright, okay, so IL max occurs when your IZ is minimum. Okay, so minimum value of RL, okay, so IL max is equals to IT minus with the value of IZ mean. Okay, how to calculate the value of IZ mean? The value of IZ mean will gonna be when it's already given in the range, which is 1 milliampere. Alright, so the maximum value of the current that is flowing, okay, IT, how much is the value of IT? IT will gonna be the value equals to the value of, okay, the value of IT will equals to the value of 20 okay, it's gonna be the value of VZ, right? So gonna be 24 minus with the 12, right? And then divided with 470, right? 0. Okay, how did you get 25.5 milliampere here? by determining the value of IT. How to determine the value of IT? Here is your IT. How to determine the value of IT? When your Zener here is turning on. So it's going to be your Kirchhoff will going to be, your current flow will going to be on this way, right? So it's going to be negative 24. Okay, 24. Okay, please write by yourself, okay? I think it's very difficult for me to write here lah. Okay, negative 24. Alah. Okay, 24. Alright, minus with the value of VR. Sorry, plus VR. Okay, plus VZ, right? Equals to 0, right? So if you find this, your VR, you can find the value of IT lah. So VR is equals to IT multiply with the value of R. Ni R. Okay, this is R here, is equals to VR, right? So you able to get your IT is equals to 25.5 milli. Alright, so this is going to be your maximum value of current. Okay, because your maximum value of current cannot be more than this value. So although the range is up until 50 milliampere, however, due to this supply voltage is only 24 volts, so your maximum current that you able to produce is 25.5 milliampere. Okay, so minus with the value of the minimum of current range 1 milliampere, so you will get the value of IL max is actually 24.5. Alright, so once you know your IL max, of course you can calculate your RL minimum. So based on the previous slides, okay, to know the value of RL minimum, when the value of IL max is load current is in a maximum value, right? So so the load current, assuming that the Zener is turning on, so 12 divided by 24.5, you will get 490 ohm, right? Okay, so this is another example. I leave this example for you to determine. Okay, if you are not able to understand this example, we will discuss this on class. And this example as well, I will leave it to you guys. Alright, and I would like to go to this when your variable, when your source voltage is vary, meaning that it is changeable. However, your load resistor is in a fixed condition. So in this case, alright, if your Vs, your source of voltage, larger than the Vs minimum, okay, then your Zener diode is turning on, so that your Vs is much larger than your Vs minimum. So if we calculate the potential difference between the source and the Zener voltage, it will gonna be the positive way, right? So that's why your Zener is gonna be turning on, so that when your Zener is turning on, your VL, voltage across the load resistance, will equals to the voltage of the Zener. Okay, so in that case, your IZ, the current of the Zener, will equals to the IZ knee, the knee current of the Zener. Okay, so in that case, what are the conditions that we need to do? There are two conditions. Alright, in this case, only one condition is constant. The IL is constant. Okay, now your IL is constant. So why your IL is constant? IL is constant because of your value of the resistance is fixed, right? So when your IL is constant, I1 equals to IZ plus IL. So this is because of the Kirchhoff current law here. So where I1, okay, is equals to Vs minus Vz over Rs, and this is happen when it is constant. Alright, this is happen when your it is constant. But now since that your Vs is not constant, meaning that your I1 also will not be constant. The only value that is constant is your IL. Alright, so how to measure your IL is by IL can be measured by using the Ohm's law, yeah. V equals to IR, because voltage across load resistor is same as Zener voltage, so we can always find our IL. Alright, if your Vs is equals to minimum, Vs is in at a very low value, then your I1 will gonna be in a minimum value. Alright, so Vs and I1 will change proportionally. When your Vs is low, your I1 also will gonna be minimum. When your I1 is minimum, alright, since that your IL is fixed, so your Iz also will gonna be minimum. Alright, but if your Vs is maximum, alright, your I1 will gonna be maximum, and of course your Iz also will gonna be maximum, because current across RL will be not change. Alright, so that is how in order these are the methods or simplified formula, okay, for us to calculate. Okay, so if your Vs is equals to Vs minimum, then your I1 will gonna be I1 minimum, and your Iz will gonna be Iz minimum as well, where the IL is constant. Alright, IL is the voltage across here, yeah. Right, so Iz is equals to I1 minus IL, and this Iz that you determine is the Iz minimum. Alright, and if your Vs is Vs maximum, then your I1 is equals to I1 maximum, and your Iz is equals to Iz maximum, and IL is always constant. Alright, so I will explain details, this example 6, 7 and others example in our next face-to-face class on Wednesday. Alright, so see you on Wednesday. Thank you.